Hi everybody. So last lecture we talked about controlling a fixed base robot in the joint space, and in this lecture I will illustrate how do we control the end effector. So how do we control the tip, for example, of a tool attached to the end of to the last joint of the robot to do some machining, to do some work. And the first easiest approach that you can do to control the end effector is to implement inverse kinematics and actually still close the loop at the joint level. This means we keep using the controller developed in the last lecture, that are joint level controller, and we just map the motion that we desire at the end effector as a desired motion at the joints. So controlling the joint motion, we can move the end effector, and to do this mapping, the mapping between an end effector motion and a joint motion is through an algorithm that is called inverse kinematics. And as you can see, for each joint, then we have a desired joint trajectory, and each controller, this is a decentralized controller, will take care of controlling the joint. Then, to measure the position of the end effector, we can check, can do forward kinematics from the joint measurements. We can get the end effector, the estimation of the end effector position. And with this approach, we know that if the joint is tracking the joint position or tracking the desired trajectory, then to a certain extent, also the end effector will track the desired end effector trajectory. This approach is very simple, and however, it requires inverse kinematics. And inverse kinematics is not like forward kinematics that always exist and closed for an analytical solution, but in inverse kinematics is not guaranteed. And what you can always do is a numerical implementation of inverse kinematics that, on the other hand, involves an optimization inside, and so it can be slow. So if you, in case a very simple case where you can have, if you can use your intuition to get a closed form solution, here in the very simple case of a 2 degrees of freedom robot, you can, using the Cosine Theorem, you can find a relationship between the end effector and this angle, for example, which is called alpha. And then compute the cosine of alpha, and you know that the cosine of alpha is equal to the cosine of theta 2. And then you can have two solutions. Already you can see if you have the elbow below, you will have a certain sine of theta 2. If you have the elbow up, you have another sine for the sine of theta 2. So then you do in the arctangent of sine and cosine, you can obtain the theta 2, and then using forward kinematics, knowing theta 2, you can work out easily theta 1. But this approach, as I said, it requires some algebraic intuition, and you can have multiple solutions, so you need to decide in the code whether you want the elbow up solution or the elbow down solution. The good advantage is that it's super fast, because it's just a bunch of equations and that's it. You have no optimization in that. Otherwise, as I said, you can rely on numerical solution techniques. How do we solve numerical inverse kinematics? Again, I take this simple example. And the idea, this is the forward kinematics of the end effector. That is the length of the first link, cosine of the first joint, plus the length of the second link, cosine of the first joint position plus second joint position. And then if you differentiate, if you do the derivative with respect to the first joint and the second joint position, Q1 and Q2, you get the Jacobian. I guess you know this quite good. And the idea of the numerical IK is to having an input, having the desired and effector position, we want to get the desired joint position. So we want to get the set of joints that are relative to that one. And for this, we consider, for example, a sequence of joint positions, of set of joint positions, and for each one we compute the error. So let's say we start from a default configuration and we compute the position of the end effector, and this position will be different from the desired one, so we compute the error between these two. And then the idea is to make this error go to 0, and then when the error is going to 0, the set of joint position will be the one correspondent to the desired end effector position. In the end, the error doesn't go to 0 never. We care about that it's becoming sufficiently small, below certain tolerance. To minimize the error, we know that we need the derivative. So with Jacobian, we can have an linearization of the forward kinematics, and we can get the derivative of the error, because the derivative of the error is derivative of the desired trajectory. In the desired point, in this case, let's see, it's a fixed point, so it's 0 minus the derivative of the end effector point, that is Jacobian minus Jacobian times delta Q. And if we don't consider infinitesimal variation, we can get the same relationship, delta E equal to minus J delta Q. Then we have we can find we can apply all this in a Newton step. This means first we evaluate the Jacobian at the initial configuration which we want to evaluate, and define in essence the linear approximation of the forward kinematics, and we want to this is the error function, let's say, computed in function of the joint positions, and the Jacobian it's like a linear approximation of this error function we saw here. So we find the intercept between this equation and 0. So we want to find the delta Q for which this is true. And then we apply, we find this delta Q by inverting the Jacobian minus 1 times the error, and we apply this delta Q, we move here, and we repeat again the evaluation. So we move here, we move here, and this will gradually converge to the desired to the value we are looking for, to the joint configuration that we are looking for. We want to stop whenever the error norm is below a certain tolerance. Otherwise, we iterate. But so this is the block diagram of this approach. Say. So we map the error at the end effector through the Jacobian in error at the joints, and then we integrate. This is in essence the integration step, and then we compute again the new end effector position and we iterate. There are some problems that you can get in this approach, and one is that this algorithm can get stuck in point where the slope is horizontal. So let's say the Jacobian in this case is 0, so it's singular, becomes singular, because if you have a singular Jacobian, you get a horizontal slope, and then you're not able to find the intercept. and doesn't you can find the delta Q value. Solution to this is to use a damped pseudo-inverse to compute the delta Q. So rather than doing the inverse of a Jacobian, we do the other term here. We do a pseudo-inverse of the Jacobian with a damping term. And this damping term ensures that a solution always exists, and the fact that this is a pseudo-inverse ensures that we will see later in a later lecture that this approach works also for redundant robots. So whenever you have more degrees of freedom than the dimension of your task space. And this is the update equation that is robust to this kind of problem. The other problem that you can have is that the algorithm gets stuck in circles. So in this case it goes here, then and the next step it goes here, back here, and it starts to cycle here. This is happening because the error is not decreasing enough. Because if you evaluate the error here and here, it's the same, for example. So a solution is to avoid cycles, is ensuring that the error decreases at each iteration, and this is achieved by moving along the Newton direction, not with a full step, but with a smaller step. So instead of doing the delta Q here, the whole delta Q, I do a percentage of that, multiplying by a parameter b that is between 0 and 1. So if we use b equal to 1, we get the full delta Q. If we take a fraction of it, we take a fraction of the step. And how do you select b? Again, I repeat the algorithm here. The b can be selected checking if you have reduction of the error. So for example here, let's say you have this nonlinear function you want to, and we have the error here. We do first, if we do a full step, which is coming from here to here, we see that the error here is this point, and in this case, when you evaluate the next iteration, the error is increased. So the error is not decreased, is not okay. So taking a full step is not good. I need to take a smaller step. So I reduce the step of the half till the error is becoming lower than the initial one. So let's say again here we take the full step, the error test is too big, it's not good. I take half of the step, b equal to 0.5. Then I evaluate the error and it's still bigger than this. Not okay. So I do another half of the step, so b 0.25, and this time I evaluate the error and I see that the error is decreased. So we can accept this as a Newton step.
For the next step again, starting from 1.
Exactly. That's why it's slow. It can be slow because you need to do all this. It's a backtracking that you do inside each Newton iteration. So it can take time to solve to get an inverse kinematic solution. It's generic. It works for every robot, but it's slow.
It could not make sense to choose one and fix the first step and then go always with that.
It depends, because if for that step the error increases, then you get in problem. You don't get.
So every time from 1 and again.
You can get that the error increases and then you don't converge, you diverge. Then there is an alternative to the inverse kinematics that was everything is clear until now? Okay. Please interrupt me if you have any question. So an alternative to the inverse kinematics is to implement a resolve the motion rate control. And this was introduced by Whitney in 1961. In essence, instead of using the J minus 1, instead of solving the inverse kinematics, directly find the delta Q that corresponds to a certain delta X. So we just use the Jacobian and the inverse of that, and this is always possible, as I said, apart from a redundant manipulator where we need to do the pseudo-inverse. And so we close the loop, this time at the end effector. So we have desired end effector reference minus the actual end effector position computed through forward kinematics. Then we compute the delta x, so the error at the end effector, and we map this delta x through the Jacobian inverse to the delta q. And then we close the loop on the delta q. So here it's missing the q value that should be summed up. But in essence, it's very simple. And as I said, different from the inverse kinematics, this time we close the loop at the end effector. So we still don't know which kind of dynamic behavior we have, but we are able to close the loop at the end effector rather than at the joint.
What is C1, C2?
C1, C2 are the controllers.
Okay.
This is controller for joint 1, controller for joint 2. It's like the controllers we have in IQ Real inside the joints, the low-level controller. Let's say you have, in this case, a position controller or a PD controller in the joint. Or it could be, if you have inverse dynamics, it could be you have coupling, so you can have an inverse dynamics plus PD. You can have whatever we discussed last lecture inside here. This approach is very simple, but the problem is that J can be ill-conditioned, especially whenever it gets close to singularity. If you have redundancy, you have infinite solution for delta Q that achieves the same delta X. And most important of everything, you have different metrics in the Jacobian. So let's say you have an error in the position of the end effector. Is measured in which unit? What is the unit we measure the error at the end effector? The linear position error. Meters. And what is the error we use to the unit we use to measure the error, the orientation error? Radians. So we have a mismatch in the metric that we use to compute the error in position with respect to the metric, to the unit that you use to compute the error in orientation. And this dishomogeneity is not taken into account here because we map everything through the Jacobian into joints. As in the case of the inverse kinematics, we don't know which kind of dynamics we are setting for the end effector, so we don't know how stiff it is. Actually, the dynamics is given by the joint controller. So if we set some proportional derivative gains, we will have a certain dynamics in the joint level. And these dynamics, if we check at the end effector, will be reflected in a certain way. And the way it's reflected is normally, even if you use, for example, constant proportional derivative gain in a joint level, at the end effector you will have a configuration dependent stiffness. It will be not a sphere but not isotropic, it will be an ellipsoid. So and this ellipsoid will change with the end effector configuration. So even if you use the same gains at the joints, because the Jacobian is nonlinear and is configuration dependent, the effect of these gains in the dynamics on the end effector is an ellipsoid, and this ellipsoid changes shape and orientation even. So it's not very nice, because ideally at the end effector we want to be sure that our stiffness, for example, is isotropic. We apply a force in one direction, and so if a force is applied in one direction, we have an error in that direction. While if it's not isotropic, you have a contact force in a direction, and the error that you generate, it's tilted. It could be in another direction. So people don't like this, especially if you are interacting with the robot. No? Think about you're pushing the robot, and this guy go on the other side. The solution to this problem is dates back to 1987, and is the work of Osama Khatib of direct operational space control. And the idea of Khatib was that instead of defining a motion for the joints, directly control the forces at the end effector that act on the end effector. So let's write the dynamics not at the joint level, but at the end effector level. Everything is clear now? Okay.
Sorry, one question. For redundancy, what can I do? Because so that
there is
a problem.
Yeah, there is a whole lecture on that, on how to solve that.
Okay.
Both at the inverse kinematics case as at the operational space.
So there's a way to deal also with the redundancy.
Yeah. But I put everything together because both cases are covered in another lecture.
Okay.
To derive this operational space dynamics, we consider it's like considering the dynamic, the behavior of the manipulator seen at the end effector. That is called the operational point. So we start from the joint space dynamics, and we map it at the end effector. How do we do that? We consider the relationship between the end effector acceleration and the joint acceleration velocity, and then we work out the joint acceleration and replace this into the joint dynamics. Okay, and we get this result. Oh, yeah. Then we pre-multiply both sides for J minus transpose, and in essence the torque becomes a force, because this is the virtual work equation that says that the torque is equal to J transpose the vector force, and then multiplying J1 transpose by what was here, you get a term that is called the operational space inertia. That, differently from the joint space inertia, M can be singular. Why? Why can it be singular?
Because you have the units of the Jacobian.
Right, because you have the Jacobian, it can be singular. While M is positive definite, and it's okay, never can be singular. Then you have something that multiplies end effector acceleration, and is we believe is going to behave like an inertia. It's operational space inertia, Plus we have very complex term that is we call mu, that contains all the bias term, the velocity from the, sometimes from some terms from the velocity of the joints, velocity dependent, the bias term due to Coriolis and centrifugal forces, and then on the other side we have the end effector force. So this is the dynamics reflected at the end effector, and these are called bias forces at the end effector. This is a complex term. You see that you can simplify replacing the operational space inertia in there, and then you have the Cartesian force at the end effector. We can underline that this is you can get this equation just projecting with J-man transpose it's the same method of projecting with J-man transpose the joint space inertia, joint space dynamics. What can we do now? We can implement the same concept that we did for the joint space controllers. So we can implement inverse dynamics. And implementing inverse dynamics means inverting this equation. So providing an input force, Cartesian force, that contains this term and inverts this, and define a new input. So the input force will have will compensate for the bias term at the end effector, and will be multiplied by an estimation of the operational space inertia. And then if we replace this force into the equation of the dynamics at the end effector, we get in essence an identity matrix x dot dot equal to Fd. So it's like our robot now behaves after the linearization as a unit mass. Now, a very important detail that I need to underline is that this term are estimated. They are very complex. They are strongly dependent on the model of the robot. In the case of lambda, there's not a big issue, apart from the singularity that you need to take care. But in case of mu, if you don't have a good estimate, it's better to set it to 0, because mu it will act as a positive damping, so it can have a destabilizing effect if you have a poor estimate, and then it can affect stability. That's why there is a reason for which people don't implement operational space inverse dynamics, and these are the reasons, because it's very sensitive to this problem. So, but the cool thing is that then we can define a new controller in FD, wherever we give the operational space desired acceleration, and we close a PD at the operational space. So we close, we have a proportional gain Cartesian. This is a Cartesian, a matrix of gains, Cartesian gains, that is multiplied by the error in the position of the end effector, and this is a matrix of Cartesian gains, damping gains, that is multiplied by the error at the velocity level of the end effector. And then if we put this inside here, we get the error dynamics, second order, that lines go to 0. So this, it's a very nice result. And how do we get the torques? Because this is the last point, right? The last point is to do Jacobian transpose F in essence, and we get the torque to send to the end effector, to the effectors. So to recap some mappings that we define here. Think always about Newton law whenever you look at this. So a force equal to inertia times acceleration. So M it's the mapping that maps joint acceleration into joint torques. M-1 maps joint torques into joint acceleration. Here we are living in the joint space world, and now when we move to the task space, we have Jacobians that map joint velocity or joint acceleration in task velocity or task acceleration. And while the Jacobian transpose is the dual that maps task forces into joint torques. And finally, we have the operational space inertia matrix. In particular, this is the inverse of the operational space inverse matrix that maps forces, Cartesian forces into Cartesian acceleration, while the inertia matrix itself maps task acceleration into task forces. Here you have the references, and till now, if you have any question? Did you know everything about this? I'm so utterly clear that you understand immediately everything, or you are too smart? One of the two possibilities. Haha. Now let's do something. It's a little bit difficult to digest, but it's useful because many people they have confusion about this. And first time I had to implement, I got a little bit confused as well. And it's about orientation. So till now we discussed about the position of the end effector. We define this force, virtual force, that is proportional to the error of the end effector and to the velocity error of the end effector. But we didn't talk about the orientation, because the end effector has a linear position but also an orientation, and you want most of the time to control both. It's because you want to place the end effector in a point to do some work, for example, and then you want to orient the tip with, for example, with the tool to be aligned with the surface. You want to machine, or you want to the gripper. You want to the object you want to grasp. So orientation control is quite important. Starting from whatever we just said on operational space control, instead of a virtual force, in case of orientation, we can implement a virtual moment. A virtual moment with torsional springs and dampers. So in this case, it's a spring, a torsional spring around Z, and the getting far from this, from the desired orientation, will result in a returning moment that tries to attract the desired orientation. So if you have one axis, you have one scalar moment. In this case, you have a linear spring. The rotational spring is just proportional. The moment is proportional. The stiffness, the torsional stiffness around Z, proportional to the times the error around Z. If you have three axes, in the case of a linear the linear case, we extend this to the vectorial form, and we have a 3D vector of force, Cartesian force, equal to the stiffness of that we said, in our controller times the error in position, which is always also a 3D vector. But in the rotational case, we have a moment, 3D moment. This is a 3D vector that is equal to some rotational stiffness. So let's say it's a 3 times 3 matrix of torsional gains, of torsional stiffness gains, times the orientation error, plus some other term, damping term, for example, times the orientation error derivative. Then, once we have these two, if you have the force, you can map them to torque, as we saw before, through the linear Jacobian. While if you have the moment, you can map it to torque through the orientation Jacobian. Now, how does the orientation Jacobian looks like? The orientation Jacobian, it's the linear mapping that, the mapping that maps joint velocity into omega. Omega is the angular velocity, the vector that represents the angular velocity of the rotation of the end effector frame, let's say, if the Jacobian is related to the end effector. And it's a 3D vector and lives in a Euclidean space. And note that this is called the geometric Jacobian, while the analytic Jacobian is mapping joint velocity into Euler Angles rate. And we will see afterwards what Euler Angles rate are and what is the relationship with omega. So once we have the moment, we can get the tau, and in general what we do, we have a PD, and the orientation error, we put a negative sign because we want to drive the orientation error to 0. So it's like saying k theta times 0 minus E0, E orientation. So it means that the reference value for the orientation is, of course, to be 0. This is the virtual moment at the end effector. In general, the orientation error derivative, because we use the angular velocity, and the angular velocity lives on an Euclidean space, it's also living in an Euclidean space. But how this orientation error is computed, because even if in the linear case it's easy, at the velocity level it's easy, at the orientation level, the orientation error really depends on how do we represent the orientation, so on the kind of parameterization of the orientation. And we have several parameterization of the orientation possible. I present only 4 of them. There's also exponential map, but for the sake of brevity, will not. The first one we'll talk is the angle axis representation. It involves 4 parameters. For this reason, it's a non-minimal representation, because you want to the orientation are 3 degrees of freedom, and we represent this with 4 numbers. So non-minimal representation. The angle axis is as follows. You have an axis element and a scalar element, and the axis element is a unit vector that is the axis about which the rotation is made. So think about this and the vector moving from this orientation to this orientation. You can find an axis that performs this orientation, okay? And this is the r-axis. And the scalar delta theta is the magnitude of rotation, so is how much you need to rotate about that axis to have the initial frame rotating in the rotated frame, in the end frame. And if you multiply both, you get a rotation vector. It is a Euclidean vector. Of course, the rotation are not commutative, so summing this is different than swapping the addendum. And if you want to map this angle axis into a rotation matrix because you need to do some other calculation, you can use the Rodriguez formula. It's just a complement. While the second representation of the orientation is the rotation matrix. So first, let me give you some introduction on the rotation matrix. There are two interpretations of rotation matrix. The first interpretation is that the rotation matrix represents the orientation of a frame if you put the axis as columns of the rotation matrix. And then the second interpretation is that rotation matrix is like a mapping that change coordinates. For example, RWBE, it's a linear operator that maps a vector from a frame, starting frame that we call, let's say, a fixed word frame, to a rotated frame B. So it's a change of coordinate. If you look at this, you have the V vector here in green that has the free component in the word frame, and then you have the base frame that is the red one rotated, and the rotation matrix just map this vector in the base frame. So the outcome are these 3 points that are coordinates of a V vector in the base frame. Everything's clear? Okay. The other, if we look at the rotation matrix, it's interesting to see that the rows of the matrix are the axis of the base frame, of the rotated frame, let's say, expressed in the starting frame. And why this? Because this can be seen as whenever you project a vector that is living in the word frame, it's like if you have the axis of the ending frame as rows, it's like you do a cross product. So you do a projection, sorry, a dot product, so a projection. You project V along the axis XB, and you get a number. And this number is exactly the component of V in the base frame. So doing this projection, you can see you get the component of V along in the base frame. While the other, if you flip these two, you can say that the columns of the matrix are the axis of the base frame, again expressed in the word frame. So if you flip the addendum, you just flip the rows with the columns. And this makes sense. Let's verify. Yes, because the output should be something in the word frame, a vector in the word frame. The input is a vector starting in the base frame, and we multiply each axis times the scalar, the component that in that frame. So the x-axis will be for the x component, the y-axis for the y component, and the z-axis for the z component. And the sum of these all are vector in the word frame. Will end up in a vector in the word frame. Now, how do we compute the orientation error with the rotation matrix? Because let's say we don't have the angle axis, we have rotations, desired orientation, and the actual orientation. So we need to think about that the rotation that maps from W, let's say we have an inertial frame here, from W to D, so this is equal to the product of the rotation matrix that maps W to A and A to D. Okay? If we right multiply for WA transpose, this term disappears, and here we have what we are looking for, which is the orientation matrix between A and D that represents our orientation error, and is equal to this expression. And now what we do with the rotation matrix, we need to get a 3D vector to compute our virtual moment for the controller. So we need to map the rotation matrix to angle axis. Yeah, you will see how to do that in the next slide. The rotation matrix, since they have 9 elements, because they are 3 times 3 matrix, they are non-minimal representation for the orientation, and the fact that they have non-minimal representation has the advantage that they have no singularity, so they're always well defined. The problem is that the rotation matrix have also orthonormal condition, 6 orthonormal condition. Let's say these are the axes, and in particular is that the axis should have one unit norm, and they should be perpendicular. So this is orthogonality condition and normal condition, and they can be expressed this way. This normal condition could be expressed like this, and the orthogonality condition could be expressed like this. So in the end, you have 9 minus 6, you have 3. So everything works properly because we need to define the orientation. So when to map the matrix into angle axis, how do we do? We follow. You have this equation that allows us to relate the trace. I think this is a trace. I'm not sure. Of the matrix to the scalar, and to get the axis this way. We need to take care of just to be sure that delta theta is not 0 in the code. Otherwise the axis is not defined and everything crashes horribly. So we need to take care that the end effect, the orientation error, is defined in the end effector frame. So if we want to the moment expressed in the word frame, let's say because we are doing everything in the word frame, we need to rotate it properly before computing the moment. Actually, in the lab I prepared, in the second lab, there's an exercise on the orientation, and I saw that everything was unstable and I didn't understand why, and because I forgot to put this rotation before mapping to torque. Okay? Everything is clear? Okay. There is something that we will use in the future that can be useful to define, and it's the derivative of rotation matrix. Do you know how does it look like?
R omega
Huh?
R S of omega.
R
S of omega.
versus times?
Times.
Times.
Skew
Okay.
symmetric matrix of omega.
Okay. Yeah. It's that, or it is omega times R?
Depends in which frame the velocity is expressed.
Okay, very good. Yes, we define in one way, just both of them are okay, depends on the frame you define omega. And everything starts from the orthogonality condition. R transpose equal to identity. So the inverse is equal to the transpose. We differentiate this and we get R transpose plus R dot R transpose times R dot transpose equal to 0. And we see that this matrix that is summed up to its transpose is equal to 0. And this is a property that all the skew symmetric minus transpose is equal to, the matrix is equal to minus its transpose. So as this is a skew symmetric matrix. Let's put it there. And we define the R dot equal to this S matrix times R, because we multiply for R both terms. This one disappears and we get this. But how does S look like? So let's go back to mechanics. Consider like a constant vector a point in that is constant in a rotational frame. So in a moving frame, there is a point in a frame that is moving, and the relative position of this point in the moving frame is constant, and this frame is rotating. Okay, so we have if we express the position of this point in the world frame, so a frame that is inertial still without moving, then we have that this expression that we said before. We map the point in the moving frame into the world frame, and if we differentiate, we get the first term derivative time this plus this, the rotation matrix times the derivative of p. But this is that we say that it's zero because it's constant in the moving frame, so we get this. So p dot w equal to r dot pb. But if we replace what we found here, r dot, we get p dot w equal to s r bw times pb. Okay, and these two are nothing else than pw. Okay, so we map the position in the base frame back to the world frame, and we have the position in the world frame. Sorry, this is a dot here. And then from mechanics, we know that the velocity of a point in a rotating frame is like this. So this is again a dot, sorry. No. So if we compare this term and this term, we see that this S is omega cross. So R dot is omega cross RB. Now, and this is equivalent to express the cross product as a skew symmetric matrix, as we said here, as this way. And we will see we'll use this in the future. Now, the third parameterization is Euler Angles. And this is very common in robotics. The Euler Angles are, the most famous one is the Tate-Bryan convention. They are called roll, pitch, yaw, where roll it's a rotation around the x-axis, pitch around the y-axis, and yaw about the z-axis. And the convention that people use most is the ZYX. So we first do a rotation around the X. To get the orientation of a frame, we do 3 rotations. One about the Z, then about the Y, then about the X. The shortcoming of Euler angles is that they are minimal representation because they are only 3. And so they have singularity. We will see that singularity is called gimbal lock. And the other problem is that they are defined in a space that is not orthonormal. So because there are subsequent rotation, you need to think, we will see, the axes are not perpendicular. But the good thing is that they are easy to be integrated. So if you do your optimization and you define parameterize as Euler angles, then you can integrate the derivative easily and get the orientation directly without doing strange things. So the Euler angles can be linked to the rotation matrix that we know very well, composing basic rotation. So we think, well, this is the rotation matrix around of a rotation about the z-axis, and we call the yaw angle psi. Then we have a rotation about the theta axis, that the y-axis, that is a rotation around the y, we call theta, and is the pitch Euler angle. And then finally we have the rotation matrix elementary rotation matrix of an elementary rotation around the x-axis represented by phi, that is the roll angle. Then we compose them, and we get the rotation, the rotation matrix that represents the orientation of the base frame, for example, in the inertial frame. And these are subsequent rotations. The gimbal lock, it's whenever, for example, you are the pitch 90 degrees, so think about this stuff moving up 90 degrees, then you're not able to distinguish between roll, yaw, and roll. So the yaw is represented by the blue, the roll is represented by the red, so you can understand that either you move, if you move yaw or you move roll, you're not able to distinguish. So you can have, for example, you can move both of them one against the other, and you get the same orientation. So more sets of Euler angle are representing the same orientation. This means that these, for example, if you do an example, these two set of angles, they result in basically the same rotational matrix. And this is a problem for your controller, because whenever you get there, you get you can get whatever number, in a sense.
Now can I see that I will have, I don't know, in the matrix some full rank deficient or something like that, or?
Good question. In essence, you can get discontinuities probably in that point, because you have an undefined output. I need to check, but the way you map the rotation matrix into the Euler angle might get you might get a division by zero in that moment, but I need to check. Sì?
Solo questo?
Sì, sì.
Pazienza.
The other point is that Euler angles have non-orthogonal axes because they have subsequent rotations. So, in essence, if you, at the beginning of my PhD, I was computing the orientation error with the Euler angles. So I was saying, okay, desired rho pitch yaw minus rho pitch yaw, get the error, map into torque, and that's it. That is wrong. It's not wrong if you have everything works if you have small orientations, because this effect is not so visible. But whenever you get with big errors, this is not correct. So that's why you need to map these Euler angles to rotation matrix or to angle axis, because angle axis, they are defined in an Euclidean space, and then you can map them into a moment and do the control. The fact that these Euler angles are not in an Euclidean frame, they means that also their derivative is not in that is not, the axes are not perpendicular, and therefore you cannot get omega integrating the Euler rate, because omega lives in an Euclidean space. But there, by the way, there is a mapping that it's non-linear and depends on the Euler angles position, so on the values of the Euler angles itself, and maps the Euler rates into omega. So you're still able to go back to do some work on the Euler angle space, and then go back whenever you need to the omega if you want. And this is what we do, because Euler angles are very comfortable to work with, especially in the optimization. Unless you don't do optimization of somersaults. In that case, you cross the 90 degree pitch and you have a problem. The last one, the last representation I'm presenting is the unit quaternions, and the unit quaternions are quite hard to digest. They are no minimal representation because they need 4 parameters. They have no singularity. This is very good, and this is why people mainly use them. But they have the problem of they need to have a unit norm. So unless they are not Euler or unit quaternions, you can understand. Try to think about an intuition for unit quaternion, thinking about how you define a point on a circle. Let's say you need what you need to define a point on a circle in polar coordinates. What are the polar coordinates? R and theta, so the radius and the angle. Okay. Then if you go to a sphere, what do you need? You need a radius again and 2 angles. Okay. And then if you go into a 2D sphere, sorry, a 4D sphere, then you get a quaternion. So you see, like, as a point into a 4-dimensional sphere where you have a scalar and 3 angles. Okay? And the scalar is put in this way. The vectorial part is called epsilon. The scalar part is mainly called W. Then you have a unit norm constraint that is completing the norm of this, or can be expressed this way. And with the Rodriguez formula, you can link quaternions to the rotation matrix if you need, using the scalar part and the vectorial part. Sorry, this is W. The inverse of a quaternion is just changes the sign to the vectorial part. So to do the inverse of a quaternion is the opposite rotation. You invert the vectorial part, and you can see that if you flip also the scalar part, you get the same orientation. So you get the same orientation corresponding to the quaternion. You can map to the quaternion also to the angle axis. For small rotation, you get this.
Having 2 quaternions with the same orientation is going to be a problem.
In general, one you can discriminate this. So you can find the one is called I don't remember, shortest radius quaternion. That in the code you discard the other one. There is one-to-one possibility. It's not a problem. This is not a principal problem that there is a singularity. It's just choosing the right one with the right sign. Then you have mapping the quaternion to angle axis, so the other way around. And the special thing about quaternions is that they follow special algebra. Let's say there is a multiplication operator defined this way, with vectorial parts of some expression of vectorial in the scalar part. And so to compose rotation, subsequent rotation, you just apply this multiplication to the quaternions that are relative to the rotations that you want to compose. So a rotation between A and B, and this is a rotation between B and C. Q3 is the rotation between A and C. So to compute the rotation error, we do something similar to the rotation matrix, and we find that the error quaternion is equal to the desired orientation quaternion multiplied by the inverse of the actual orientation at the end effector, because the transpose is like this, like doing the inverse. And then if you apply the multiplication operator to this, we get this expression. That is what people use to do usually orientation control, because then from the orientation error quaternion, from the quaternion error, you can get with the angle axis mapping the orientation error, and from there you can get the virtual moment for the controller. Okay, I think we can do a break here before the next session. Do you have any question? Everything is clear? Okay, let's do 15 minutes break, and then we continue with the